So let's carry on in Chapter 3. I think this may be the last lesson in Chapter 3, we'll see. And review what we learned at the end of the last lesson about atomic radius. So I sketched a little summary from the end of the last lesson to remind you that radius increases as we read top to bottom of any column or group on the periodic table, and radius decreases as we read left to right across any period on the periodic table. This is going to play out to be pretty important. So, can we look at a set of 3 atoms and, based upon their location on the periodic table, rank them in order of increasing size? So, get your periodic table out, pause the video, and see if you can put these 2 sets of atoms in order from smallest atom to largest, because we're going in increasing size. So there you have my answers for this. You notice that these first 3 are all in group 2, and so they increase in size from top to bottom. These 3 are all in period 2, and so they decrease in size as you go from left to right. We're going to draw a couple of big generalizations here that are going to be helpful to us as we make comparisons about how different atoms behave. Okay? First thing we're going to say is metallic atoms, because they tend to be the larger atoms. They have lower ionization energies, okay? And there is a weaker attraction between the nucleus and the outer electrons of these atoms. These atoms tend to lose electrons easily. We can generalize and say metals are good electron losers. On the other hand, nonmetals are essentially the opposite of this. They tend to be smaller with higher ionization energies and stronger attractions between the nucleus and the outer electrons. And the result of that is that nonmetallic atoms tend to be good electron gainers. We'll talk more about that as we move forward. And this is a pretty safe couple of generalizations. Will metals always lose electrons? No. Will nonmetals always gain? No. But when nonmetals and metals get in each other's neighborhood, most of the time, the metals lose electrons and the nonmetals gain them. And that's going to be a very helpful generalization. So now we should talk about writing electron configurations for ions. We actually talked about this. It came up in class when we were going over one of those practice questions well over a week ago. And, you guys seemed pretty sharp on how you might write an electron configuration for an ion. And if you think about this, all you're going to do this is adjust the number of electrons according to the charge. Okay? Let me do the first one here. Sodium, the atom, has 11 electrons. Okay? And would have a configuration of 1s2, 2s2, 2p6, 3s1. With a positive 1 charge, we are now talking about a particle that has 10 electrons. 1 electron has been lost, and so we're going to write the electron configuration and remove the outermost electron for a configuration of 1s2, 2s2, 2p6, or essentially the same as neon. So I would like you to pause the video and do chloride and sulfide, if you would, and then restart and we'll see how you did. So as you can see in both of these cases, we have gained electrons. Chlorine has gained one to make this particle called chloride, and thus has this configuration, which can be written as just argon. It is now got the same electron configuration as argon. And sulfur has gained 2 electrons to make sulfide. The name does change, there's a suffix change. And 18 electrons, same as argon. When 2 particles have the same electron configuration, they are called isoelectronic. So you could say that the chloride ion and the argon atom are isoelectronic. They have the same electron arrangement. So give aluminum +3 a shot. The aluminum +3 ion has only 10 electrons. It's lost 3, and its electron configuration is isoelectronic to neon. Now these iron +2 and iron +3 ions down at the bottom of the page are a little bit different. So how about you draw for me the electron configuration of plain old iron first, and then we'll see what changes. So here is the electron configuration of the iron atom. So to make this ion, we are going to remove 2 electrons. And to make this ion, we are going to remove 3 electrons. Now, this is something that we haven't, I think, literally said in the past, but I'm going to call your attention to these, which are my valence electrons. And the valence electrons are always the first ones removed. So we've been talking about valence electrons for most of this chapter, chapter 3. And when we have a variety of electrons in an atom, we always remove first from the outermost shell. So the electron configuration for the iron +2 particle will be argon 3d6. And for the iron +3, it'll be argon, I have to take one more electron away, which will leave me with 3d5. So sometimes you will read a statement that will say something along the lines of, this particular atom is more metallic than that particular atom. Okay? Or this particular atom is less metallic than another. What we're talking about here is that general behavior that we defined a couple of slides ago. Metallic character is defined as a tendency to lose electrons. Some metals do this better than others, and it has to do with their size and their ionization energy. So the larger atoms are better losers than atoms that are slightly smaller. So to answer this question about which in these pairs of atoms is more metallic, you really want to go back to the ionization energy trends and the atomic radius trends to answer that question. So let's pause the video here and ponder this a little bit and see if you can choose of these various pairs of metals which would be a better electron loser. And I think you're going to want your periodic table for this. So pull that out as well, if it isn't already. So by comparing radii based on their position on the periodic table, I hope you and I agree with our choices. This is a table that is found in your book. It is figure 3.40. This is definitely one for you to photocopy or print or whatever and put in your reference folder, okay? This table shows us the typical ion charges for various elements based on where they're located on the periodic table. So if you look at this column here, all of these in group 1 are metals that are good losers. They all have only 1 electron in their outer shell. And so loss of 1 electron for those tends to render them fairly stable. They are rendered stable because if they lose one electron, their electron configuration is isoelectronic to a noble gas. And we know that noble gas electron configurations are pretty stable because noble gas atoms don't bond. They don't lose electrons. They don't gain electrons. They don't share electrons. They are in a pretty good situation with the electrons arranged just like that. Likewise, group 2, having only 2 electrons in the outermost shell, tend to be good losers of 2 electrons. If you go over here to the nonmetals, you can see that group 17, the halogens, they're very good gainers, but they gain just 1, so that they are isoelectronic to a noble gas. The oxygen group tends to gain 2, and the nitrogen group tends to gain 3. Carbon, I'm going to put this one in parentheses. Carbon is not a very good electron gainer or loser. In a rare instance, you might see it losing or gaining. And aluminum makes sense, I think, because if it loses 3 electrons, it becomes isoelectronic with neon. And there are a few others here that have definite charges. Okay? And I will highlight the zinc and the silver. And there are many here that have multiple charges possible, like the iron we just diagrammed, chromium, gold, mercury, copper. Okay? You want to have this page handy because anything that shows up as only one possible charge, that's pretty much its charge all the time if it's an ion. Now be careful. These are ion charges. These are not charges on atoms. Atoms have no charge. Remember, atoms have a charge of 0. Their protons and electrons are the same. So don't glance at this table and misinterpret it as if we're talking about atom charges, because we are not. Our final slide in this lesson is writing formulas and naming simple binary ionic compounds. Binary means that the compound is made of 2 elements. The compound is ionic, so these will be made from a metallic element and a non-metal element, a metal and a non-metal. And this is how we write their formulas. The metal is mentioned first in the name and has a charge that is positive. The non-metal is mentioned second in the name. The suffix is changed to "ide," and that particle has a negative charge. So if you refer to the ion table that I just showed you, you will see that a sodium ion has a positive 1 charge, a chloride ion has a -1 charge, and when you put them together, they make the compound sodium chloride. It's important that you keep in mind that when we combine the ions, that we are combining sufficient positives and negatives to create a net zero compound. Sometimes we need multiples of the positive or negative piece so that the charge nets out to 0. Let's take a look at aluminum bromide. The ion charges are Al3+, Br1-, and they combine on a ratio of 1 aluminum for 3 bromides for a net zero compound. So I'm going to pause. I'd like you to pause here and see if you can write the formulas for the remaining compounds. I hope that you and I agree. And if we do not, or you have questions, raise this in class or pop in and see me at CCL.